Hello everyone, I am Kushagra Khullar. I am from the Department of Electrical Engineering. Our team consists of Anubhav Prasad, Amrta Chaurasia, Vatsal Venkatkrishna, and myself. We are here to present our term project for the Artificial Intelligence Foundations and Applications course 2022. We have identified a few research problems based on human-robot interactions that were of great interest to us and tried to understand the ideas and AI techniques that have been used in them. The first problem that we have focused on is robot guide dog. Let's understand the problem statement first. So why do we need robotic guide dogs? As we all know that the guide dogs are very helpful for guiding elderly and visually impaired people. For that, they need to be trained well. The problem here is that the training is very time, cost, and labor intensive, and moreover, not all the dogs are qualified to serve the purpose. Another problem is that the skill cannot be transferred from one dog to another. Therefore, to achieve the objective, we can replace the dog with a robot so that we'll be able to use the same algorithm for all the robotic guide dogs and can mass produce them. The cost is also comparatively affordable, and we can use different AI techniques to better serve the visually impaired people. Now, using robots to guide humans is a long studied problem. However, there are several issues with the already existing robotic frameworks. Like most of the previous guide robots have large foot bases, which makes it very difficult to guide a person in narrow spaces. Also, most of the previous work uses rigid robot arms for guidance, because of which the system may get stuck in the narrow regions. Also, it adds more degree of freedoms and needs extra effort to design. All these previous papers couldn't solve the problem with narrow spaces. Now, this paper has addressed this problem by introducing a small robot that could guide humans with a leash. The advantage of using leash is that it can become slack, which allows the robot to change the internal dimensions of human robot system to find a better configuration to lead humans to pass through these narrow spaces without collision. The leash can be either slack or taut. Firstly, we'll introduce a physical human-robot interaction framework, and then we develop this hybrid model to capture the dynamics of robot-leash-human interaction. This hybrid model is then used in the path planning to safely guide humans to avoid obstacles during navigation. Now let's first introduce physical human-robot interaction model. The ability of the robot to understand the current human-robot system configuration and to interact with human via leash is very important for guidance and path planning. Therefore, this model is needed to capture the state of the human-robot system. The human-robot configuration is shown in the figure here. Here x comma y is the robot's position, and xh comma yh is the position of human, and L is the length between human and robot, and EL is the unit vector from human to robot along the leash. Whereas theta is the orientation of robot in world frame, and phi is in robot's body frame. Also, this hybrid dynamic model has two modes, taut mode and slack mode. Let me explain the taut mode first. Here we are assuming human will always hold the leash and will move in the direction of the force applied by leash when it is taut. But when the leash is slack, human will not experience any force and won't move. Hence, this hybrid system is defined by the system states Q equals to x comma y, which is robot's 2D position, theta, phi, and L, leash's length. We also define the robot frame attached to the robot body. Then we can define the robot velocity in inner body frame. The input to this system includes robot velocity and angular velocity. When the leash becomes taut, the hybrid dynamics can be formulated as shown here. Here, alpha values are the respective discount coefficients which are introduced when leash goes from slack to taut to compensate for tracking errors which occur due to the external disturbance caused by human-robot interaction. Now, Anubhav will take up from the next part. Thank you.
Thanks, Kushagra. My name is Anubhav Prasad. So, coming to the slack mode. When the leash is in the slack mode, then the hybrid dynamics for the system are given by the following set of equations. Here, only the robot is moving. Human is assumed to stand still since the tension in the leash is not present. Leash tension model. This was done by simply mapping the generalized coordinates to the leash tension, which allows consideration of physical interaction during the path planning. To capture the relation between generalized coordinates and leash tension, a linear regression model was constructed to minimize the mean squared error loss between robot speed and leash tension. Leash tension model is given by the following equation. Hybrid transition modes. Since taut leash is almost analogous to a rigid arm, hence in confined spaces such as narrow corridors with sharp 90-degree turns, the leash must transition to a slack state. The following hybrid system was considered from the transition. Here we can see that S subscript T represents the taut state and S subscript S represents the slack state. When the unit vector along the leash, that is E subscript L, and the unit vector along the direction of the robot, that is E superscript P, the dot product is greater than or equal to 0 and the leash tension is greater than or equal to a minimum value that is given by F bar, then the system is in taut state. Here this minimum value minimum F bar represents the maximum intrinsic leash tension when the leash is in slack mode. Below is the figure that represents the model in different states, and the arrows represent the transition from taut state to slack state and slack state to taut state. Path planning. This figure shows the framework of the system. Goal position is fed as an input to the global planner. We get the current and goal coordinates generated in the path from the global planner. We then define the cost function as follows, which is to be minimized. This cost function is represented by the following equation. Here the first term, that is q norm of qn minus q target, represents the quadratic terminal cost, which tries to minimize the deviation of the final node from the target position. Second term allows us to find the optimal travel time for the robot motion instead of using a fixed value. The third term, that is norm of uk, minimizes the control input. Fourth term minimizes the least tension while ensuring a smooth change. Fifth term brings us the faster optimization convergence, and it tends to have more dot nodes. Obstacle avoidance. In this paper, the obstacle avoidance was considered for both the robot and the human, but the two simple sign distance constraints are imposed on them. This capital Xk superscript obvious comma j represents the 2D coordinates of the jth obstacle at kth time. We then have the following two constraint equations. Equation 12 represents the constraint for robot, and equation 13 represents for human. Here R superscript h and R superscript obs represents the robot, human, and obstacle dimensions. A safety margin parameter of d is also added. Quadrupedal robotic guide system framework. Planner is composed of a search-based A-star global planner and a collocation-based local planner. Global planner. For global planner, search-based A-star planner is used over a grid map on a reduced generalized coordinates given by x, y, and phi. The continuous transition on nodes on the R3 configuration is defined as delta x, delta y, and delta phi. The node cost and heuristic cost at any node is defined by the following equations. Equation 14 represents the node cost, and equation 15 represents the heuristic cost. This A-star global planner generates a continuous collision-free trajectory with a sequence of 5-dimensional waypoints. This is passed to a local planner. Robot localization and human tracking. First of all, an occupancy grid map is built with a 2D lidar based on Hector's lab. To estimate the position of the guided person, a depth RGB camera is used to detect humans' 3D position through OpenVINO. And a Kalman filter based on a constant speed linearized system is applied to track the detected human position. The camera is deployed on a 2 degree of freedom gimbal which can rotate and pitch, and it is programmed to keep the guided person visible in the camera frame irrespective of the relative orientation of the human with respect to the robot. Velocity tracking controller on Vinicitta. Since the model was implemented on Vinicitta, existing state-of-the-art velocity tracking controller was used here, where the MPC computes desired reaction forces, foot and body position from the given velocity commands, and from these forces, WPIC model computes desired joint position velocity that are delivered to joint level controllers to generate joint torques. Next, Vatsal will present human motion prediction.
I am Vatsal Venkatkrishna, roll number 19CH30037, and I will be focusing on the topic of human motion prediction. So, comprehending and predicting human motion is crucial in assisting humans and machines to interact in the outside world. Predicting future human motions is an innate ability for humans to interact with other people, such as shaking hands, navigating crowds, or defending against offensive players in a game. Hence, the issue of human motion prediction is of great significance and a challenge to modern computer vision and machine intelligence. For fluent and safe human-robot interaction, both the robots and the humans need to be able to anticipate each other's actions. Bayesian deep learning approaches can help model trajectories in an online setting, and these models can also help in sampling trajectories and in inferring targets. Robots need to be able to identify human actions on a macro and a micro level. To put it concretely, the robot needs to be able to identify the action of grasping an object and the exact trajectory and velocity of its movement. Hence, online analysis of the current human motion is not sufficient, and the robot needs to be able to identify human motion and actions, and it needs so that it can initiate appropriate actions in time and allow for long-term planning as well. Most prior work only incorporates knowledge about the current configurations of a system and do not anticipate human motion dynamics. They also depend too much on the training data and cannot generalize well to novel targets. Here's where the paper Anticipating Many Futures, Online Human Motion Detection and Generation for Human-Robot Interaction comes in. This paper was submitted in 2018 to the International Conference on Robotics and Automation, ICRA, and this paper uses conditional variational autoencoders that are trained to predict a sequence of future human motion given a window of past frames. It is a probabilistic generative approach, and it generates a latent space which can be used to sample, which can be sampled from to generate future predictions. Using skeletal data obtained from RGB depth images, this paper proposes an unsupervised approach which can be used for online motion detection for up to 1660 milliseconds. Traditional autoencoders use an encoder-decoder mechanism, which aims to reconstruct the input from a latent space, thereby making it a low-dimensional representation of the input. However, the latent space is discontinuous and unregularized, and hence this latent space cannot be used to draw samples, and more often than not, it will generate garbage values. So a variational autoencoder aims to regularize and constrict the distribution of the latent space to a Gaussian, most likely a Gaussian. And this allows someone to sample from this distribution and hence makes it a generative model. Coming to the data set used by the authors collect skeletal data of the joints in the upper body and observe the joints that are listed in the image. They observe 100 minutes of arbitrary and general movements like walking, dancing, waving, and split it into an 80:10:10 train test validation split. The RGB renditions of each frame of the video were taken and used as the dataset. Coming to the approach, the main idea is to predict a window of frames at future time steps given the past time steps. The likelihood of a variational autoencoder depends on the data from only a single observed variable and hence doesn't fit into the vision of predicting future time steps given the past. Hence, the authors propose to use conditional variational autoencoders, where the three elements HE, HT, and HD are represented by fully connected neural networks, and the inputs are represented by the variable X given the time step T and T-1, and similarly the hidden variables are represented by Z in the image. Coming to a conditional variational autoencoder or CVAE, it is basically a generative model which is conditioned on past observations, and the input is encoded into a distribution over the latent variables by a neural network. Samples are then drawn from this distribution to make predictions on future trajectories. So the generative process consists of an encoder HE, a transitioner HT, and a decoder HD with the respectively. At each time step, the encoder maps the previous input and a sample from the prior to the encoded state ET, which is then passed into the transitioner to encode hidden variable dynamics. The resulting state is then decoded into the probability distribution over the observations xt, and a sample is drawn from this output distribution denoted by x hat of t. The results that the paper shows are outperform previous work by quite a bit, and the graph that has been shown on the slide represents the maximum motion prediction error of the torso, arms, and arms over time, which shows that the uncertainty grows with time, which means that as time increases, its deviation from the given arm position increases. The authors also test online target prediction using sample trajectories to infer one of 4 targets. The model is able to do so within 500 milliseconds, outperforming previous work by a lot. Due to the latent distribution of the CVAE, different possible future movements can also be sampled, which are in line with the observed path trajectories. Now, coming to this video, which was provided by the authors, this can be helpful to understand what exactly the model can do. So, at each time steps, the future trajectories are predicted for each joint for the next 1660 milliseconds. The yellow dots represent the prediction for each joint and further into the future. And as you go further into the future, the dots go further away from the current position of the joint. That's it from my side. I'll be handing over to the next person right now.
Hello everyone, myself Amrta Chaurasia, roll number 19EE10004. I'll be discussing the paper Interactive Robotic Grasping with Attribute Guided Disambiguation. The paper got accepted in 2022 IEEE ICRA conference. The motivation behind the paper is, we know that increasing need of robot-human interaction is there, and natural language as an interface is a powerful tool in robotic manipulation such as grasping. We also know that language is inherently ambiguous, thus robot needs more attribute information to perform the task precisely. Attribute-guided POMDP is the solution that is proposed that sequentially plans asking and grasping actions based on the reports. Now briefly, let's see what POMDP means. POMDP is partially observable MDP where the agent cannot directly see the underlying states, but the important fact being that it models a system which has limited observation and can also model real-world sequential problems and processes such as robot navigation problem. Formally, it is a 7-tuple SATR, omega, O, and gamma that depicts relationship between agents and its environment. We'll see how the authors have used this in detail. Now let's see how our approach is novel compared to other approaches tried previously. The existing approaches exclude candidate objects and ask for fixed questions only, such as, is this the object you are wanting? They model yes-no responses to discard the correcting response and also sample single words from entire dictionary. Whereas attributed guided PUMDP uses target and attribute scores to calculate expected return of attribute based or pointing based question. And based on this information, it accurately and efficiently gives us the result. Coming to the system overview, let's discuss the system overview walking through an example. Here is a user query, give me the apple to eat. And here is a scenario where there are few things, few fruits, apple, green apple, pear, banana, and few other objects. The object detector classifies the object, annotates the object as its in its attributes, and forms the candidate object class. It is now fed to object grounding, a module that provides us the grounding results, which essentially is the matching scores corresponding to each candidate objects. We can see that there are various matching scores for each object, few being on the higher end. Now to resolve between the high matching scores, it goes to attribute guided PUMDP planner. So it sees the attributes that are color, such as red and green, and location, that is middle, left, and so on. Since the matching score for these three are highest, we need to ask question to the user to resolve among them. First question being the attribute based one, which is what's the color, red or green. So once the user says it's green, the matching score for these two green things is higher than the red one. And then we need a pointing based question to ask the user if this is the correct one to finally grasp the object. Method used here are first component being object grounding. They utilize MATNet framework that comprises of image encoder CNN and text encoder LSTM. Query language Q is along with candidate objects XI are used to train MATNet to predict the matching score. Matching score is given by weighted average of 3 modular scores corresponding to subject, location, and relationship. A relationship as in color. The matching score of an candidate object given a query Q is given by the formula. The color predictor uses MATNet ResNet CNN encoder that predicts the probability of 10 most common color values. The author used color words extracted from RefCoco dataset. RefCoco dataset is also used for training for matching scores. The last function that is used here is binary cross entropy given by the formula. Now coming to the second component, attribute guided disambiguation. Disambiguation is based on PUMDP model that is defined as 6 tuple. Essentially it is 7 tuple, but the authors have just utilized the 6 variables. X being the state space, that is a set of candidate objects containing the target object that we have to find. T is the deterministic transition function. A is the action space consisting of ask attribute, ask point, and grasp. Ask attribute asks for attributes based questions such as what is the color, is it red or green, or the location, is it right or isn't right top or right bottom. Ask point ask a question that has a boolean input from the user, whether this is the object you are looking for with the pointing gesture. And finally the grasp action grasps the object and gives it to the user. R is the empirically designed reward function that motivates the agent to find the target quickly. Here we can see various reward values for each action. Asking attribute gives the reward of -1, 0.1. Ask point is -0.3 as it is more specific and more information dependent. Grasp XB, where XB is the target object, gives the highest reward, and grasping an object which is not the target object gives us the lowest reward. Omega being the observation space consisting of all possible user responses, and O is the observation function that is equal to the per object conditional probability corresponding to a question. We will see how this function is calculated. Observation model is used to calculate them. For an attribute based question asked at ATR, we sample words from color, vocabulary such as red, green, blue, and or location vocabulary such as top right, top left, bottom, middle for conditional observation O and sample attributes values. It is calculated using the following expression. Whereas for a pointing based question, we get binary responses from the user. So when the system is pointing to an object xi and the user responds to the question whether this is the object as yes, then the probability of xi being our target object goes to 1 and the other object goes to 0. Whereas if the user responds as no, the probability of the pointed object goes to 0 and the other one as 1. Finally, we have to update the belief. So in the system, we maintain a belief over all the candidates to make action decisions sequentially. In the system, belief is initialized with the matching score to reflect the initial confidence, and following each answer to each disambiguation questions, the beliefs are updated. Let's see how this happens. Let's see a few experiments. Here is an example of disambiguation on RefCoco containing similar items. So these two items are more or less similar, looking similar. So in each case, we visualize the ambiguous objects with matching scores and outstanding attribute values. Blue bounding boxes denote preferred target items, whereas red bounding boxes denote the most matched objects by the object bounding module. Our module corrects the matching mistakes by asking attribute-based question and content-based question to resolve between the various items. Finally, coming to the real-world experimentation, here we can see there are a few cans, and the user asked for a Coke can to drink. So in the very beginning, all the objects have a similar belief score, but with each question it gets updated. So for the first question is based on the location of the target object. So when the user says it's in the middle, we have 3 objects in the middle. So our belief of 3 objects raises and all other dies down. Then still there are 3 and we have to classify further. So the second question is asked where again 1 is going down to 0 and other 2 are still remaining to be decided on. And finally on the last question, that is the pointing based question, the belief goes to 1 and for the other it goes to 0, and finally the system grasps the object that has belief 1. Now let's see the evaluation scores. The experiment was performed on various baselines, and the system proposed is having the highest success upon trial ratio, thus the highest accuracy. And we can also observe that the questions asked per assignment is the lowest for this new approach. And these are the accuracy benchmarks. These are the links to the paper that we have discussed, that our group has discussed. Thank you.